Welcome to the second Abaqus tutorial as part of the 2071 Mechanics of Solid Materials class taught by Professor Lala Anand as part of the Mechanical Engineering Department at MIT. In this second tutorial, we're going to be looking at an Abaqus study of the tension of a plate with a hole in it. So this is analogous to section 9.4.3 in the course textbook. And in the video today, we're going to look at reproducing this problem in Abaqus. And actually, we're going to compare the results that we get from the Abaqus FEM solution to the analytical solution and see how good of a job it does. All right, so the problem setup. On the left, you can see we have this square plate. So it's 100 millimeters on each side. And we're applying a far field loading condition of 50 megapascals on the upper and lower surfaces. This small hole in the center of the plate is going to be a radius of 3 millimeters, and we'll refer to that hole radius as A later on in the slides. On the right, you can see the actual modeling approach that we'll be making in Abaqus. So we're going to actually be doing a 3D model this time. So we have an out-of-plane thickness of the plate of 2 millimeters. And even though we are actually modeling the 3D shape of the plate, whereas in the previous tutorial, we took advantage of axis symmetry to just make a 2D planar model of a rotationally symmetric object. In this study, we're still going to be taking advantage of symmetry, but we're going to be using it to model only a quarter of the plate. So you can see this upper right quadrant of the plate is what we're actually going to be modeling. That's the part shown in dark green. And the remaining 3 quadrants shown in sort of translucent green, we're going to be including just through symmetry boundary conditions on this upper right quadrant. So for the material of the plate, we're going to consider an aluminum type material. And we're going to treat it sort of as a generic aluminum with elastic, perfectly plastic material properties. So we're going to use a Young's modulus of 72 gigapascals, a Poisson's ratio of 0.33, and an initial yield stress of 300 megapascals. Now in this table here that's reproduced from the course text, you can see some representative values for different alloys of aluminum, where you can see that the stiffness of each of them is 72 gigapascals, so our number is spot on. And the yield stresses range from 275 for 6061 to 503 megapascals for 7075. So our value of 300 megapascals is sort of on the lower end, but a reasonably representative value. Also of note, we have some fracture mechanics properties for the different aluminum alloys. So we have K1C, R1C, and L star, but we're not going to be using those for this tutorial. And just a quick note on the modeling approach that we're going to be taking in Abaqus. So Abaqus has no built-in units. You may have noticed in the previous video that when we put in values of the Young's modulus and loading and the actual dimensions of the specimen itself, you never specify what units you're using. It's actually just up to the user to make sure that all the quantities that you enter are internally consistent. So we have to do a little bit of work to really ensure that we know that the units that we're entering are internally consistent. But given that you've done that work, it's kind of nice to be able to choose to use whatever unit system is most convenient for the problem at hand. So here below, I've written out 2 of the really common unit systems, where on the left you have the standard metric system, so base units of meters for distance, kilogram for mass, second for time. And this gives you derived units of newtons for force, pascals for stress, joules for energy. But on the right, you can actually see an equivalent system constructed in terms of millimeters, grams, and milliseconds, where the derived unit for force is still newtons, but stresses, which are going to be newtons per millimeter squared, are megapascals, just naturally. And the energy comes out as being Newton millimeters. And so here, for our problem, since we're going to be working with stresses that are in the megapascals and dimensions in millimeters, the millimeter, gram, millisecond system is going to be most convenient for us. So for example, this Young's modulus value of 72 gigapascals, we'd put in 72,000 because it's 72,000 megapascals. And this yield stress of 300 megapascals, we would put in just a value of 300 rather than in the past video, if you're working in meters, kilograms, and second, you would have put in 300 E6, 300 times 10 to the 6th power. And so now that we've gotten those notes out of the way, we can look at the analytical results that we're going to be comparing to for the stress distribution about a hole in a plate. So at the top, you can see the expression. So we have sigma theta theta, that's the circumferential value of the stress. And we're looking at it as a function of r. And at this specific inclination, pi over 2, and that's defined with relative to the direction of the far field applied stress, which we're calling sigma theta, or sigma infinity. So here in the diagram, you can see the far field applied stress is vertical, and the ligament of the plate that we're going to be looking at the stress distributions along is inclined at this angle of pi over 2 to that vertical direction of loading. And we come up with this expression, which you can see derived in the textbook, for sigma theta theta normalized by sigma infinity. So that's a stress concentration factor. And it's a function of A, the radius of the hole, and R, your radial distance from the hole. And from this analytical expression, we get that familiar stress concentration factor that you may have encountered before, that at R over A equals 1, which is the surface of the hole, we have a stress concentration factor of 3. So the circumferential stress at the surface of the hole at this particular inclination is 3 times the far field applied stress. In our specific example, we have sigma infinity of 50 megapascals. And so our sigma theta theta max value, which is what we're going to be observing in the FEA simulations, is 150 megapascals. And this stress concentration factor, the sigma theta theta over sigma infinity, is going to rapidly decrease to 1 as R increases, which is equivalent to moving away from the surface of the hole into the body of the plate, which is an example of St. Venant's principle. So here at the bottom right, we have a plot of the stress concentration factor, sigma theta theta divided by sigma infinity, varying from normalized radial coordinates, so R over A, from 1 to 10. So you can see at R over A equals to 1, at the surface of the hole, we get this value of 3, which we're familiar with. And then very rapidly, as you move a few of the initial hole radius values away from the surface, the sigma theta theta value approaches sigma infinity. All right, so now let's move on to modeling and see how well Abaqus can do at reproducing this result. Okay, so we're here in Abaqus CAE, and we're going to get started modeling this problem. So to be clear, because this is the second tutorial, I'm not going to go quite as slowly as the last tutorial. I'm going to move a little bit quickly, assuming that you've picked up the general workflow of how we go about modeling from that previous video. So let's get started. We're going to create our part. This time it is going to be a 3D part. We're just going to call it plate. It is going to be deformable, and it's going to be a solid extrusion. So that essentially just means we're going to sketch a 2D sketch and extrude it out of the plane. That works well for our upper right quadrant of the plate that we'll be modeling. And so does this approximate size for our sketch. So 200 millimeters, again, because we are working in millimeters as our base unit of distance, this 200 means 200 millimeters. And our plate that we're looking at is 100 by 100 millimeters. So this is a good size. Now my PC has some trouble opening up the sketch module at times, so you'll forgive me if I fast forward through this part. Okay, so the sketch module has finally opened up, and let's sketch our geometry. So for this quadrant of the plate, we're going to be sketching a 50 millimeter by 50 millimeter square, which then has a 3 millimeter radius quarter circle removed from its bottom left corner. So we're going to start with the rectangle tool, the first corner at 0, 0, the second corner at 50, 50. Again, because we're working directly in millimeters, this is convenient. We can just type in the number 50 and it means 50 millimeters. So we have our square, 50 millimeters by 50 millimeters. And then in this lower left corner, we're going to draw a circle centered at the origin. So we click for the center at the origin, click somewhere along this bottom line to choose the radius of that circle. And then we're going to use the dimensioning tool to write that the dimension of this circle's radius is 3 millimeters. Okay, and now we have our 50 by 50 millimeter square plate with a 3 millimeter hole in the lower left corner, but we have to go about removing all these extra lines that remain. So we'll zoom in here at the intersection of our circle and our square and use the handy auto trim tool to remove these extra ligaments. And what we're left with is our quarter plate geometry. So we're satisfied with this. We'll hit the done button, and this is the sketch for our solid extrusion. Now, the extrusion itself only has one parameter needed to define it. That's the depth of the extrusion. So as we noted in the PowerPoint slides, we're going to be doing a 2 millimeter thick plate. So the depth of our extrusion is 2 millimeters. And here's our quarter plate geometry. So that's the end of the part sketching process or the part modeling process. And we'll move on to property. Similarly to last time, we'll define our material using this material editing dialog. We're going to name it aluminum, and we're going to give it those elastic and plastic properties that we defined on the slides. We'll choose linear elasticity, give it a Young's modulus of 72,000 because that's 72,000 megapascals, 72 gigapascals. The Poisson's ratio is 0.33. It's dimensionless, so we just type that in as is. And then for plasticity, we go to mechanical, plasticity, plastic. The yield stress is 300 megapascals. And we can just write one table entry at 300 megapascals yield stress and 0 plastic strain. And this will fully define our perfectly plastic material. And so we're done defining the elastic plastic properties of this aluminum. So the next step is to create a section which will have those aluminum material properties that we can then assign to our actual 3D geometry. So we're going to name the section aluminum. It's going to be a solid homogeneous section. And it's going to have those aluminum material properties that we just defined. And then finally, we'll assign that section to our part here. And because this is essentially the whole domain of the part, I'm just going to name it all. Okay. And so now our part has turned this lovely turquoise color, meaning that we've successfully assigned our material properties to the section and the material section to the part. So we move on to assembly. Here in assembly, we're going to click the create instance button to insert an instance of this plate part that we just created. And before we leave the assembly module, I'm going to create some sets and surfaces that we're going to use for applying our boundary conditions. So here, under sets, I'm going to create a bottom set, which, as you may expect, is going to be the bottom of the part. This is going to be used for applying one of these symmetry boundary conditions. Similarly, we need a left set, which we're going to choose as the left face, which is going to be used for another symmetry boundary condition. And then finally, of course, we need a top surface, which we're going to use to apply a pressure corresponding to the applied stress. Applying pressures in Abaqus requires a surface not a set, because surfaces have associated surface normals, which defines the direction for a pressure. So we're going to create a surface called top, and it's going to be the top of our part geometry. And so now we can click these surfaces and sets that we've created, see them highlighted in the viewport in 3D, and confirm the bottom set is the bottom, the left set is the left, and the top set is the top. Now, just applying these symmetry boundary conditions and the loading is a problem purely in the plane. So we need some constraint that keeps the part from freely displacing in the z direction. And we'll actually just apply that at one of these nodes along the bottom surface here, just to keep it from, just to dampen out that rigid body translation mode. But we're not going to create a set for that. We're just going to apply that directly on one of the vertices of this part. So then we move on to this step. We'll create a step. We'll just call it load. General static step is perfectly adequate for this scenario. We don't need nonlinear geometry or stabilization. Again, we're going to define a time period of 10 so that we can then limit the increment size to 1 and then expect to get 10 frames of output. The only thing to note that's a little different here is because we were using the millimeters, grams, millisecond unit system, this actually corresponds to 10 milliseconds of loading time. But because we're just doing a quasi-static analysis anyways, time has very little physical significance here, and so that's perfectly fine. We're going to ignore the interaction module for now. In future tutorials, we will use interactions, but not necessary for this study. And then we'll go to load. And actually for applying the loads and boundary conditions, I prefer to use this steps menu in the subtree on the left. So if you go to steps, you click on the plus symbol to the left of it. You can see we have an initial step for applying 0 boundary conditions and a load step, which is the one that we just created. So in this initial step, we will indeed apply some of our 0 boundary conditions. So the symmetry that we require, we're going to have xsim, as in symmetry about the plane defined with x as its normal. So we're going to choose a mechanical symmetry type boundary condition. And we're going to apply it to this set that we created for the left surface. And of course, we're going to choose the xsim boundary condition option that's built in, which just enforces symmetry about the x direction. And then similarly for the bottom surface, we're going to create a ysim boundary condition. So we can select this bottom set as our boundary condition set and choose the ysim built-in option so that we now have symmetry about the y direction on the bottom surface and symmetry about the x direction in this left surface. And as I was mentioning previously, we do need to constrain one of these vertices in the z direction just to keep this part from flying off in the z direction due to an unconstrained rigid body mode. So we'll pick one of these nodes. I'm going to create a boundary condition, which will be zfix, let's call it. And I'm going to pick the displacement option. And rather than picking a set, I'm going to select in viewport, select this node back here. Don't need to bother creating a set for it. Hit done and say use 3 so that we don't get a rigid translation mode in the 3 direction. Okay, so then now for the load step, as a load, let's add the pressure to the top surface. That corresponds to the applied tensile far field stress. So we'll call this load. Actually, let's give it a better name. Let's call it sigma infinity, because that's what it is. It's going to be a pressure. It's going to be on the surface that we've previously created called top. And it's going to be minus 50 in magnitude. So a 50 megapascal pressure pointing outward, which in this case, as you can see, corresponds to tension. Okay, so now we've set up the boundary conditions for our boundary value problem. And the next step is to look at the mesh. So in this problem, I'm going to take advantage of the comparisons that we'll be drawing between the FEM results and the analytical result to also demonstrate for you the effect of using different types of elements and of being clever about setting up our mesh. So first, just to sort of get things started, I'm going to take a sort of naive approach to meshing. I'm going to use many of the sort of default options that Abaqus will spit out for you and see how well that compares to the analytical solution. And then from there, we'll make a few progressive refinements to get closer and closer to that analytical result, and hopefully in the process learn something about finite elements. So let's start with that sort of naive approach. We're going to switch to the part here so that we're meshing on the part instead of on the assembly. And we're going to hit this button to seed part and just use the default approximate global size that Abaqus gives us of 2.5. That's fine. And you can see a reasonable number of elements. For most of the part, these default global seeds will do just fine. But you may have noticed around the curvature of this hole, it only wants us to use 2 elements, and that doesn't approximate a hole very well. So here, around the surface of the hole, we are going to add our own seeds. A good rule of thumb is that 8 elements is good to resolve reasonably well a quarter of a circle. So we're going to just stick with that for now. And you can see we now have 8 elements along the circle. And then also a good practice for 3D finite element models is never to just use one element through the thickness of such thin structures like we're seeing here. So if we mesh this right now, we can actually do that. You can see we have this reasonable looking mesh, nice and uniform, with a reasonably well resolved quarter hole and 2 elements through the thickness. So actually I thought it was only going to make 1, but it looks like it's made 2 elements through the thickness for us. So that's good, and we're happy with this mesh, and we can move on to running the study. Actually, before we do that, let's examine the element type. So our mesh looks good, but we always have to keep in mind the actual type of element that Abaqus is applying. So if we go to the element type menu here, we can see that we're using standard 3D stress type elements that are linear and reduced integration. We actually want to switch that to hybrid formulation. It's always a best practice in static studies to use hybrid elements. And just keep in mind that we're using linear elements for now. Okay, so then again, we're going to skip optimization. We're going to move right on to job, and let's create a job. We're going to call this tension. We don't have to play around with any of the job settings. The default ones will do just fine. And then let's get started running it. So I like to run my jobs here through the job menu in the tree, the modeling tree. So you can click the plus button next to jobs, and then the tension job, you can see right click it, hit data check, always a best practice to do a data check before you fully run the job. So we've submitted the check, and we can actually monitor it to see the check's progress. You can see it's finished processing the input file, It started up standard and it's completed, and we pass the check. So then let's submit the actual job. It's going to tell me job files already exist. That's okay. We submit it and we monitor. And we should see up here that it'll take 10 steps of 1 millisecond each, corresponding to the 10 steps that we requested in our step setup. And indeed it did. Took them all quite quickly, all at once. And so let's take a look at the results. And so here you see our mesh again. Just to emphasize the symmetry, I'll actually reflect this geometry about the symmetry planes so you can see the full thing. So if you go to View, ODB Display Options, and then choose Mirror/Pattern, we want to reflect about the YZ plane and the XZ plane. And if we do that, we'll see our full plate with the hole geometry. And then if we look at the contours on the deformed shape, we can see some nice contours of the Mises stress that corresponds to the contours that you would see on the full geometry. Now let's switch to S22, so the 2-2 component of the stress. And actually along this particular ligament that we're interested in, the 2-2 direction, or the sigma YY, corresponds to sigma theta theta, the circumferential stress that we're reporting in our analytical result. So this peak value of 115 megapascals is, in theory, what we should be comparing to our stress concentration peak value of 150 megapascals, corresponding to our far field applied stress of 50 megapascals. So already you can tell that we are under predicting the severity of the stress concentration that is actually occurring on the surface of a real life plate with a hole. But we can get a better look at the actual finite element approximation along that ligament to the analytical result if we export the distribution of stresses along that ligament and then plot it, doing some post-processing in MATLAB against the analytical result. So let's do that. So here, I'm going to get rid of these symmetry reflections and just show the actual simulation domain again. And let's zoom in and sort of focus on that ligament from which we're going to be extracting the results. So this bottom surface. So here, what we're going to do is we're going to create a path variable along this ligament from which we can then export those results of interest for post-processing. So if you go to path, create a path, we're going to call this ligament. It's going to be an edge list. And then for viewport selections, you can hit add before, and we can select in the viewport the actual path of edges that we want to be included in our reporting process. So you can see as I hover over each element, it's highlighting in orange one of the edges of that element. And we have the option to choose edges individually, or in this case, we can save a lot of time by selecting edges by feature edge. And so if we click here, you see we get the entire feature edge starting from the inner surface of the hole on the plate and ending with the outer surface of the ligament. And this corresponds to that the coordinates of theta equals pi over 2 and r from 1 at the surface of the hole, and then growing large as you move away from the hole. Or r over a, rather. So done with this path construction, we can then go to XY data and create to export data from that path. So here we have several options to create XY data for plotting or export purposes. History output and field output are very common options here. But right now for this application, we're going to be using a path variable. And so XY data from path menu shows up. We've selected this ligament path that we've previously defined. And the current step, frame 10, so the end of the analysis with the fully applied boundary conditions, is where we're going to be exporting the data from. And the field output variable that's currently displayed in the viewport is the one that we're going to be exporting along the path. So that S22. And if you click the plot button, you can see a preview of the actual data output that we're going to get from this process. On the y-axis, you have the stress in megapascals, which you can already tell is taking on its peak value of around 112, 115 megapascals, severely under-predicting the theoretical result of 150 megapascals. But to get better clarity on how this compares with the analytical solution, we're going to export these data into MATLAB and co-plot them with the analytical solution, which will then give us a lot of insight into how changing our mesh can improve our approximation of the analytical solution. All right, so we're going to choose to save this data as sigma TT, and then because these are linear elements, I'm just going to call it lin. And this doesn't export the data, but it saves it as a XY data variable over here on the left, which you can see I can double click to plot. And if I choose this XY curve options for sigma TT lin, I can change the color of the line. I can change the style of the line, the thickness, and I can choose to show the actual data symbols. But if I want to actually export the values of these data symbols, the way that I do that is going to report XY sigma TT lin in the XY data tab. So that's the data that we just created. And then if you go over to setup, you can choose the name and the location of where you want to save this file. I have a Dropbox folder set up for this demonstration, and I'm going to save this first file as just linear.rpt. These options, the default options, are usually fine. Essentially what Abaqus does is it'll generate this RPT file is just a text-based file, sort of like a CSV, but it doesn't actually use commas to separate things. That essentially just contains a table of the raw data values of the XY data that you selected. So here we're going to get values of the true distance along the path as the X coordinate and the stresses as the Y coordinate. The only option that you might have to watch out for is this append to file option. So if I already had a file named linear.rpt in this directory and I had append to file selected, rather than overwriting the pre-existing file, it would just add the new data to the end of the pre-existing file, which in certain contexts you may want, but I generally don't want that option. And it at least is good to be aware that that's the default and think about whether you want that option selected or not. Okay, so then we hit OK, and it'll write that data for us. And you can see the XY report was written to a file in my Dropbox called linear.rpt. And so now I'll switch over to MATLAB and let's do some plotting. Okay, so here we are in MATLAB. I pulled up the same file to which I saved that linear.rpt report file. And I've also pulled up a plotting script that I've written to co-plot the FEM solution from Abaqus and the analytical solution. So I'll quickly walk through what this is doing. This import data function in MATLAB is really excellent at importing these RPT files that come out of Abaqus. The one thing to keep in mind, though, is that if I just run the import data function, what it gives me is a data structure type variable. So I can look at this and it gives me a data variable, which actually includes the numeric values of the data that we exported from Abaqus. And then it also has text data and column headers as separate members of this data structure. So in order to actually pull out just the numeric values that we're interested in plotting, my usual approach is to take that data structure that results from import data and do data1 equals data1 dot data just to get that numeric array. Okay, and then we have A, the value of the radius of the hole in the plate, and then a linearly spaced array of R values, which we then plug into this analytical function, which is the previously shown expression for sigma theta theta normalized by sigma infinity. And that is our analytical result, which we then coplot with a scatter plot of the FEM results that we just exported. Okay, and when we run this script, here's what we see. So in black, we have the analytical solution, the expression that was previously reported on the keynote slide, and then the red X scatter plot points are the FEM solution that we just reported from Abaqus. So now, as you can see, the red scatter point plots are actually not terribly far off from the analytical solution, especially far away from the hole. They do quite a good job of approximating the analytical solution. But then in this very stiff region, as you approach the surface of the hole at r over a equals to 1, you get progressively worse and worse approximation from these evenly spaced linear elements, which then at the surface of the hole does a very poor job approximating that stress concentration factor. So you can see we have a stress concentration factor closer to about 2.3 than the analytical result of 3. So let's return to Abaqus and revisit our mesh and see a couple of simple steps that we can take to improve the quality of this result. Okay, so we're back in Abaqus, we're in the mesh module, and the first thing I'm going to do is change the way that the seeds along this ligament of interest are distributed so that we can actually keep the same number of elements along this ligament, but just give them a little bit of bias towards that inner surface of the hole so that we can get better spatial resolution where the steeper spatial gradients of the stress are. And by tailoring our mesh to the expected result in that way, I'll show you that we can get a much better approximation of that analytical result. For this case, actually just to keep things nice and regular across the whole 3D domain, I'm going to select all 4 of these ligaments on the symmetry surfaces leading up to the hole and give them all the same bias that I'm going to apply to the pi over 2 ligament. So we have 19 elements based on that sort of default naive seeding that Abaqus gave us, and we're going to stick with that 19 elements. But what we're going to do is we're going to give it a single bias. So previously it had no bias. What we're going to do is give it a single bias and bias it towards the surface of the hole so that, like I was saying previously, we get more elements where the variation in the stress spatially is larger. So the arrows indicate the direction of where the more refined elements will be according to this biasing procedure. So these arrows on the bottom surface we want to flip. So we'll select each of those so that those edges have element spacing that's biased closer to the hole. So we'll give it a bias ratio of 20, which is decently large, as you'll see. And that gives us these progressively finer spaced elements towards the hole. So that looks nice. It's going to warn us that this invalidates our old mesh. That's fine. And actually what we'll see is that, so this green coloring on the part denotes that it's using a structured mesh, which gives us a very neat and organized looking mesh. But with this biased seeding that we've done, if we actually mesh the part with this structured mesh, you can see that the aspect ratio of some of these elements near the hole are a little bit unideal. And so actually what we're going to do in this scenario is switch to sweep, which then gives us this yellow colored mesh. And when we then mesh this part with the sweep method, we can see it's not quite as neat, but the aspect ratio of these elements closer to the hole is a little bit neater. It's a little bit more even. Although what it has done is it's eliminated the two elements through the thickness of the plate. So we'll have to add a seed here through the thickness with no bias, just telling it that we want two elements along that direction. And now this mesh is one that we're happy with. So again, we have biased spacing leading up to the hole, so that in theory, we can better resolve the spatial variation of the stress as we approach the hole. And just for completeness, let's again check our element type. We haven't switched from what we were using previously, but I just want to remind you that we were using these standard 3D elements, linear in geometric order with a hybrid formulation. Okay, so let's run this job. With the new mesh, we can monitor the job. See that it's completed the analysis input processor, started up standard. And this one should run nice and easy, just like the last analysis, because we really haven't significantly changed the number of elements involved. We kept that 19 elements along each of the ligaments constant. We just changed how they were spaced out, and you can see, again, it easily runs through all 10 steps. We can view the results, see a similar spatial distribution of the Mises stress, but in this case, the peak value is much closer to that 150 target that we're looking at. Of course, we're comparing S22 to that 150 value. We can also see that it is closer. We're at around 143. So we still haven't quite resolved that 150 number, but we're getting better. And just to get a good sense of how well we're resolving the analytical solution along this whole ligament, let's export the data and plot it against the analytical solution again. So quickly, let's create the path. Gonna add before, select by feature edge, which again, by selecting this first edge, will then give us the whole feature edge that we're interested in. Okay. And then we can create XY data from the path along the ligament. We want S22 during frame 10. Looks good. And let's first just plot it. And we can already see that the spatial variation is smoother and that the peak value is closer to 150 relative to our initially evenly spaced mesh. So we know we're doing better, but to get a more quantitative sense of how much better we're approximating the analytical solution, let's export the data. We'll call this one sigma TT bias. And then again, we'll go to report, XY, sigma TT bias. And we'll call this one bias.rpt. And we've exported our RPT file. I'll quickly swap over to MATLAB. And you can see the bias RPT file has popped up. So let's choose that one. And you can see that we've gotten much, much closer to that analytical stress concentration factor of 2.83. So previously we were around 2.3, and now we've got 2.83. And that's with the same number of elements along that ligament. We've just spaced them out so that they're more even, more closer spaced where there is more spatial variation in the stress. So again, we've significantly improved our approximation, but there's still room for improvement. And a simple way, very simple way to improve these results is just to change to quadratic elements, as you may have guessed. So we're going to return back to our mesh. We actually don't have to change our mesh at all. We can use these same element nodes, but just change the type from linear to quadratic. So here in the element type, we're going to choose quadratic, not reduced integration, hybrid formulation. And then we're done remeshing. We've just changed the element type, not the actual mesh, which is very simple. We can submit the job, hit OK. And now though, because we have quadratic order elements, we've effectively doubled our degrees of freedom. So it's a significantly more complex problem. And it will take a little bit longer for Abaqus to compute. Here you can see it's actually taken 5 steps in the first chunk and then 10 in the next chunk. So still quite fast, but you do notice the increased computation time of switching to quadratic elements. And then we can take a look at our results. Switch to S22. And actually, it's going to tell us 154.8 megapascals is the peak value. However, this is not an accurate reflection of the stresses that are going to actually be reported when we use our path output. This is just an extrapolation for visualization purposes of the maximum value that doesn't actually reflect the internal maximum value that Abaqus is reporting. So disregard this number for now until we actually export our path variable data. Now, conveniently, because we didn't change the mesh, our path variable from the biased linear elements is still perfectly fine to use. So we go to XY data, create, path, plotting along this ligament path, S22 in frame 10. We plot it, and it looks nice. Hard to say just from this alone exactly how well we're approximating that stress concentration factor. So let's export it. Following our previous convention, we'll call it sigma TT quad. And then we'll go here to report once again, XY, sigma TT quad, setup, and we'll name this file quad.rpt. And we've exported quad.rpt to the Dropbox. Switch over to MATLAB. Quad has shown up. And we plot it, and we see we've done much, much better, much closer to that analytical value of 3. Our quadratic bias-spaced elements have gotten us a stress concentration factor of 2.927. And actually, if you look at the match between these other values of the FEM solution versus the analytical solution, we're doing a little bit better there than for the linear elements as well. So overall, the quadratic elements gave us a very, very simple way to improve the fidelity of our solution without even changing the mesh. Okay, so we're briefly going to summarize the conclusions from the different mesh studies that we've done for this hole in a plate problem. So we started with linear, evenly spaced elements. And here again, you see the plot that we constructed for the comparison between the FEM solution for the stress field distribution leading up to that hole versus the analytical solution in black. So even though far away from the hole, our linear elements were completely adequate for approximating this analytical solution, as we reach those steep spatial gradients in the analytical solution near the surface of the hole, our linear elements with even spacing did not do a very good job resolving those sudden changes. And this resulted in a 23.4% error in the FEM solution's approximation of this stress concentration factor at R over A equals 1, the surface of the hole. It's pretty significant. So as a first step to attack that error, we then stuck with the linear elements, but added some biased spacing so that the linear elements were spaced closer together where we expected there to be steeper variation in the stress field. So by doing this, again, we've overlaid the FEM solution in red with the analytical solution in black. You can see that the approximation of the FEM solution in this steep ascent region of the stress field is much improved versus the evenly spaced version. And in fact, our approximation of the stress concentration factor at the surface of the hole only has 5.7% error using these bias-spaced linear elements. And then as a final simple step that we could take to improve our approximation of this analytical solution, we switched to quadratic order elements, but kept that same exact mesh with the bias spacing as in the second case. And here in this case, just by increasing the order of the elements, we got a significantly improved approximation to the analytical solution at the surface of the hole. We only had a resulting 0.9% error, which is quite a good approximation of the analytical solution. And you can see that even throughout the other regions of the analytical solution, our FEM solution does quite a good job approximating that analytical result. So the next thing we're going to do in this video, satisfied with our approximation of the elastic analytical solution, is put our loading in a little bit into the plastic regime and just see what kind of behavior we can observe in our plate with a hole in it as it enters that elastic plastic behavioral regime. Okay, so as a final part of this video, I'm going to show you a little bit of what happens if we load this plate with a hole into the plastic regime. Recall that we defined our aluminum material as elastic perfectly plastic with a yield stress of 300 megapascals. So to do that, I'm just going to simply change our boundary condition from 50 megapascals to 200 megapascals. So recall that the stress concentration factor near the surface of the hole is 3, so we expect that the peak sigma theta theta resulting from this loading will be 600 megapascals. Now, sigma theta theta is not the same thing as the MechE stress, but it is safe to assume here that if our sigma theta theta is 600 megapascals, the MechE stress will end up being at least greater than 300 megapascals. So we'll hit OK. And having made this increase in loading, let's rerun our job. So this is, of course, still with the biased mesh. I can show you. We're still using this mesh, which we've specialized to the steep spatial variation in stress that we expect near the hole. And it is still with quadratic elements. So now let's monitor the job status. We expect, for one, since we've used quadratic elements, that again, it's going to take a little bit longer to compute. And then you can see here, under total iterations, it's taking more than one iteration in some of these steps. And that indicates the onset of the plastic behavior. So plasticity is a little bit more complicated to compute than elasticity. So you can see the total computation time is greater even than the simply elastic study with the quadratic elements. So let's now open the results and take a look. So here again, we see our upper right quadrant of the plate. If we click this rainbow button to plot the contours on the deformed shape, the default that it'll show us again is the MechE stress. And you can see it has a peak value of around 322 megapascals. Now again, I'll suggest that this is an artifact of the extrapolation that Abaqus does in order to actually visualize these contours on the body. We wouldn't expect that the MechE stress inside the body would ever take on a value above 300 megapascals because it's elastic perfectly plastic, which means that in the post-yielding regime, we never expect the MechE stress to rise above 300 megapascals. And indeed, we can zoom in a little bit on the MechE stress distribution around the hole. And we see this constant region in red, which would indicate the region where the MechE stress has reached that limit value of 300 megapascals. To get a better sense of this picture of the spatial distribution, we can actually plot the MechE stress along our path variable, following the same procedure as shown previously and along this same ligament, which we've previously set up. And we can see, as we've expected, that we get this similar sort of steep increase in the stress leading up to the surface of the hole. But that then as you enter this plastic deformation region near the surface of the hole, the MechE stress is hanging out right around 300. We do have a little bit of numerical noise so that it's not exactly 300 in this whole plastic region, but you can tell that it's enforcing that elastic perfectly plastic response by keeping the MechE stress approximately at 300 megapascals in this entire plastic deformed region. And in fact, we can view contours of the equivalent plastic strain by going up here and selecting PEEQ. So that's plastic E is plastic strain, EQ is equivalent, so it's the equivalent tensile plastic strain. And you can see indeed the regions in blue have 0 plastic strain, and then you get non-zero values of the plastic strain here near the surface of the hole where the MechE stress takes on its highest values. We can also plot this quantity along the path. To see that indeed the equivalent plastic strain is 0 outside of the regions where the MechE stress has reached its limit, its yield stress of 300 megapascals. And then inside the region where the MechE stress has reached 300 megapascals, you get non-zero values of the plastic strain. And physically, you get an interesting manifestation of the plastic deformation here at the surface of the hole. If we can arrange our view here, you can see by cycling through the frames, let's get rid of this ligament, that at the onset of the plastic deformation, the plastically deforming regions start to do a dramatic lateral contraction. So the change in the thickness of the plate in these plastically deforming regions is significantly larger than the change in thickness of these non-plastically deforming regions. And this is because plasticity is fundamentally a volume preserving process. It's, as we would say, incompressible. So as the plastic strain evolves and these elements elongate in the direction of the applied loading, they must also contract in order to maintain their current volume during the process of plastic deformation. So that's an interesting physical insight that you can get from the Abaqus simulation that would be much, much harder to derive from an analytical result. So that's all the content we had for this tutorial. And so to conclude things, I'm just going to summarize everything that we've covered in the video today. So first, we constructed an Abaqus FEM simulation of a plate with a hole in it in tension. And then we took the results of that simulation. We exported a spatial distribution of the stress data from the Abaqus results for post-processing. And then we used that exported data in MATLAB to co-plot the analytical solution with our FEM solution, and then used that comparison capacity to get a sense of the benefits that we derive from using a clever biased approach to our element spacing as we approach the hole, and then just the simple fact of changing the order of the element formulation. And then satisfied that we've done a good job approximating our analytical elastic solution, we then explored a little bit of the plastic response of the plate with a hole in tension and used that to get a good sense of how plasticity would come into play in such a study in the real world. And with that, that's all the content that we wanted to cover today. I hope to see you in the next tutorial, and thank you for watching.